Welcome back. In the previous lectures, we had seen the open mapping theorems. Now, continuing along the direction, so it's several variable case, we are going to look at the inverse function theorem and implicit function theorem in this lecture. This lecture will be the last lecture of this course. So, what is the statement of the inverse function theorem? So, the inverse function theorem tells you that if you have a map F, which is a continuous map, which is a map which has continuous partial derivatives, which is from the domain omega, which is a subset, open subset of Rn, and it's a map from omega to Rn. So it's a map from Rn to Rn where the domain is omega, and F admits continuous partial derivatives in omega. Now, if at some point A in the domain, the determinant of the Jacobian matrix is non-zero at A, then there are neighborhoods around A and its image f of A on which the function is a bijection. That is, for any p in V, you have a unique x which solves this equation. So you actually solve this equation for all p in V, right? And if you remember, this is how we started 2 lectures back. So the main question was, how to solve this in the nonlinear context and so on, right? So here we are giving a kind of local solution. So for all p in V, you can find an x in U. Further, this, because it's a bijection, this inverse f inverse exists, right? Because it's a bijection, so f inverse will exist, and that f inverse is continuously differentiable. So when I say C1 here, I mean continuously differentiable. So let's look at the proof of this. So the Jacobian, so determinant of the Jacobian matrix is, because the determinant map is just nothing but like a polynomial, right? So when you say jf of A is non-zero, by the continuity of this determinant, we know that there is a ball B1 centered at A such that for all points of B1, j of x is non-zero, right? So the property of continuity, something is non-zero at a point, then there is a neighborhood around that point where it is non-zero. Now we have already seen in the previous lecture, right? When you have a function which is, I can show that by this theorem, where it says that when you have a function such that the j of A is non-zero for some A, then there is a ball on which this is injective. So the given function is injective. Only condition required is continuous partial derivatives. We have that hypothesis in our theorem, right? So there is a ball around A on which f is injective. Yeah. So by that theorem, we have that there is a ball B2 which is centered at A such that f is injective on B2. Okay. Now on B2, f satisfies all the hypotheses of theorem 54, the one that we proved before for open ball, right? Like for open set, we had proved the statement that whenever you have f continuous partial derivatives exist and f is injective on the set and the Jacobian is non-zero at all points, then f of u is also an open set for the open set, right? So you apply this for B2. Okay, so if you apply this on B2, you get that f of B2 is an open ball containing f of A. So now you set this u to be the B2, and that's the u So we have to find a u and v on which f is a bijection, right? Right. So we set this b2 that we have obtained as our u, and we set v to be the image of b2, right? So v is b2. Now by our construction, f is bijective, right? Because f was already injective on b2, and we define v as image of b2, so this is a bijection, right? So f from u to v is a bijection, and f of b2 is actually an open ball, so this v is actually an open ball containing fa, right? So fa is here and a is here. So we need to show that we anyway have to show that f inverse is continuously differentiable, right? We first show that f is continuous. F inverse is continuous, but that's kind of easy, right? Obvious, because we have shown that f is an open map, right? By the theorem that we have, like, let's see here, open mapping theorem here, we have shown that under continuous partial derivatives, if the Jacobian is non-zero for all x, then f is an open mapping. That's precisely what we have here, right? F inverse, f is actually an open map on u because f is Jacobian is non-zero for all points of u. Okay, and by construction, f inverse is unique because it's a one-to-one map. We have only one. The bijection that we have obtained is just inverse of that, right? So we have an unique inverse, and that's continuous. What we need to show now is continuous differentiability of f inverse. So for that, what we do is that whatever we did in the previous lecture theorem, um, we just take, if we take any n points in omega, we kind of concatenate these points in Rn square. So now there's an n square tuple, where the first n tuple is the x1 point, the second n tuple is the x2 point, and so on. So we have n square, so that you call as z, right? So we did a similar argument in the previous proof, right? In the last lecture proof. So we are just repeating that argument here to prove that this is continuously differentiable. F inverse is continuously differentiable to prove that. So repeat that argument. So you take the z, which is a concatenation of these n tuples of this, right? Now, so z has n square elements. Now you define the function h, whatever is the domain, right? Because basically you need to take the domain such that all x, these x's are coming from omega, right? So it's more or less the domain. So so the domain of h will be any point such that each of its n tuples there should belong to omega. Only then this will make, this definition will make sense, right? Because fi of xi should make sense. Fi of xi will make sense when xi is in the domain of omega. So there is an appropriate subset in Rn square on which h is defined, and h of z is defined as determinant of that matrix. And I've already said this is not the Jacobian matrix, right? Because this xi changes in each row. Now this is a continuous function because it's a determinant function, which is a polynomial. Now, like before, you take capital A as the concatenation of the vector A. So you have n square A, right? A is an n tuple. So you have n copies of A in n square. That is your capital A, right? Then h of A is jf of A, which is given to us to be non-zero. Therefore, by continuity of h, there is a neighborhood. There is a open ball. Am I using the same omega? Yeah. Yeah, so this omega is different, okay? That there's a okay. It's actually this should be some. So there is some open ball centered at A such that h of z is not zero for all z in that open ball. So this omega is not this omega, okay? That was That's a mistake. I should have used a different notation here. Okay, so there is some open ball centered at capital A such that h of z is not equal to 0 for all z in that open ball. So with the argument that we already gave in the previous lecture, that if h of z is non-zero, that means this determinant of this is non-zero. For here for all z, that means for all xi that you can choose from omega, that means dj fi xi is non-zero for all xi in B. More or less, you can think of B as the projection of that ball onto one of the R, because Rn square is Rn Cartesian product n times, right? So you can think of this as a projection into one copy of Rn of this open ball that you obtain here. So dj fi xi is non-zero for all xi in B. So the whatever B2 that we have chosen here, so we had chosen a B2 from this theorem, right? From this theorem 55, you can choose an open ball B2 in B1 centered such that F is injective on B2, right? This B2 could have actually been chosen as contained in this B, right? Because this B is again something centered in omega, so you can just choose a B2 such that it's contained in B, okay? In fact, you can choose such that you can B2 closure is contained in B. Then we have dj fi xi is not equal to 0 for all xi in B2 closure, right? Because this is true for all xi in B, so in particular it's true for all xi in B2 closure. So we need to show that we are doing all these things to show that Fn so this F inverse is continuously differentiable. So just to avoid complicated notation, we just call this as G. So we need to show that G is continuously differentiable. So the V that we had obtained, which is the image of B2, right? If V was defined as image of B2, right? So the image of B2, image of B2 under F, right? The one that we chose, the way we chose here, V is F of B2. So that is open, right? So that's how we had obtained it as an open ball. So for any V in this capital V, there is for very small t, V plus t Ej, because in open set V plus t Ej will belong to V. Ej is the jth canonical basis of Rn, right? This is a subset of Rn, right? So V plus t. So you can choose a very small t such that if you do this translate, that is still in V, right? Now you define U to be the image of G under V. So basically it's F inverse of V. G is F inverse, right? So F inverse of V. So the F inverse of V, which is now in U, right? And you define U prime as the image of V plus Tej. So you take an element V, you translate it in a way, in a very small way, in a up to a small t, right, along the jth direction. Okay, so this is a translation along the jth direction, right? So you do that such that it's still in V. That means you can compute g of V and g of V plus Tej, call them as U and U prime, which are sitting in capital U. Now what is f of U prime? See, G is the inverse. So f of U prime is f composed with G, f inverse, f composed with f inverse, which is actually V itself. So f of U prime is V plus Tej, f of U is V. So subtract that, you get Tej. So this is actually V plus Tej minus V, which is Tej. So f of U prime and f of U is this Tej. Therefore, for each I, right, for each I, you have this formula. Why? Because fu prime minus fu is Tej, right? This is an tuple, right? This is an f was a map to Rn, so this has n components. This also has n component because this is Ej vector, right? This is a t scalar ej is a vector where this is 0 everywhere except at the jth position you have 1. So if you match the component wise equality, right, component wise, you get that fu prime fi u prime minus fi u over t is 0 when I not equal to j, and when I equal to j, that is the jth position, you have 1. All right. So now by mean value theorem, for each I, there is an xi in the line joining u prime, right, uh, such that fi u prime minus fi u is grad fi xi u prime minus u by t, right? This is by the mean value. So this is a one-dimensional, right? So one-dimensional mean value theorem that we are using. It's on a line, straight line joining the vector. So you have xi. See, these are vectors, but I'm looking at, we are applying mean value theorem on the line joining the, on these two vectors, right? So you have, there is an xi such that this happens. This is the mean value theorem. Now what you do, this is this we know from this formula here is either 0 or 1 depending on what I is, right? So this is basically ej, right? This is precisely ej. So what we have is, this equation is nothing but dkfi, which is this dkfi xi u prime minus ut equal to ej, which is coming from here. Okay, so this is precisely the system of equation. So you have some matrix on some vector equal to something. So we need to solve the system of equation, right? So you use the and this is solvable if the determinant of that matrix is non-zero. So you use Cramer's rule, and you actually solve for the Lth unknown, right? Yeah, I mean Lth unknown. You have system of equation, right? You have n unknowns, right? So you, for the Lth unknown by the Claymores formula, you actually get this formula that so u prime L minus ul by t is equal to this, where Al is the matrix djfxi, where the Lth column is replaced by ej, right? So Al is that you replace the Lth column by the ej is the source, this term here, the given term here, right? So this is replaced in this matrix in the Lth column, and that, right, that's the part which is part of the Cramer's rule, right? And this is precisely where the definition of ul prime and ul is precisely this, which is gl of this. So we have this formula, and this is true for each L. Now you take limit t going to 0. So if you take limit t going to 0 here, you see this is nothing but the derivative, the jth partial derivative of gl. So the jth partial derivative of gl, t goes to 0, right? And here when it t goes to 0, if you actually notice, this al depends on this u here, right? So when t goes to 0, this ul prime actually approaches to ul, because you see this u and u prime are like this. So, and when t goes to 0, the u prime will get closer and closer to u, right? I mean, this xi is coming from here, right? So, and this xi will also move towards u. So when limit of t going to 0, whatever we have here, this becomes the al. So alu is this matrix where you evaluate this matrix at not xi but at u, where the Lth column is replaced by ej. Okay, and here determinant xi will be replaced with u, so this is nothing but jf of u. So this is the formula that you get for the partial derivatives, jth partial derivatives of gl. So the partial derivatives of g exist and is continuous because it is quotient of continuous. This is a determinant function. This is also the Jacobian function, right, which is again determinant. So they are just kind of quotient of continuous functions, so they are continuous. Okay, so that kind of finishes the proof of the inverse function theorem. So what did the inverse function theorem say? Actually, the inverse function theorem tells you that locally you can invert this function. You are given a function, and if the Jacobian is non-zero, then you can find neighborhoods around that non-zero Jacobian point where you can actually invert the function. Locally, you can invert the function, is what inverse function theorem tells you. So it may not be invertible globally, but it can be inverted locally under these conditions. So just to show that, so recall that a curve in a plane is not always graph of some function. So it cannot be expressed as a function. For instance, the circle in a plane, right? The unit circle in a plane is not graph of any function, right? Because for any x, it's multivalued. It's not even a function, right? If you take the full circle. But the point is, it's locally a circle, and that's what inverse function theorem has told you, that though these are not functions, locally they can be seen, though these are not graphs, locally they can be seen as graph. So functions are locally as graph or local graphs. Locally they are like graphs. So for instance, take the circle function, take this function fxy, which is x square plus y square minus 1. So this is precisely the set of all, so circle is precisely the set of all x and y such that f of xy is 0, right, in R2. F of xy is 0 is the equation corresponding to the circle. Now you take any point x0, y0 on the circle such that y0 is positive. So what we mean is that we are taking any point on the upper, any point on the circle which is on the upper half plane. Now if you set gx to be root 1 minus x square, because now you are restricted to the upper half plane, which set gx to be 1 minus x square and y0 to be g of x0 for all y0 greater than for all y0 greater than 0, right? Now, so locally, that is, once you fix this point x0 and y0, then locally, uh, so in the upper half plane, this g actually denotes the circle on the upper half plane, right? So it can be expressed as a graph of the function g, the upper half plane part of the circle, right? So we can actually have very small neighborhoods u and v naught of x naught and y naught respectively, right? Because that is where it's kind of mapping. It's taking the domain as u and giving v, and that graph of that is basically the circle which is lying on the upper half plane. Okay. So any locally you can make it as a graph of a function. The same argument also holds in the lower half plane, but you just choose this negative square root of 1 minus x square. It's going to tell you that the lower half plane can be seen as a graph of such function, right? But this is again, but there are points, and in both these cases, if you notice, fy of x naught comma y naught is because y naught and y naught. In both these cases, fy of x naught comma y naught, that is, you just differentiate this with respect to the y variable here. So it's 2x. This is 0, 2y and 0. So it's just 2y naught, which is non-zero because y naught was either chosen positive or negative. Now what are the points for which this is not satisfied? If you take y naught to be 0, right, that is x naught, if y naught is 0, what are the possible choices on this line? When y naught is 0, minus 1 comma 0 and 1 comma 0 are the only possible points with y naught 0 on the circle. So on these 2 points, you see this condition is not satisfied. Fy of x naught and y naught is not 0, right? This condition is not satisfied, and here you cannot, there is no function g such that you can write y as a function of g, right? Locally you cannot invert it. There is no map which will show it as a graph of function, right? Because you see this, you are in the circle at the end. On these 2 points, any neighborhood you take, it's still multi-valued, like before, like in this case, right? Okay, so that's the thing about, so that's the importance of this condition here. So what we have shown now is that when this is when this is not zero, you can locally see it as a graph of a function, and when zero, in this case at least we have shown there is no g, right? But the zero case is actually in terms. So in the previous example, one may have local in kind of explicit form at a point where f of z is not zero, a fact we shall prove in more generality in implicit function theorem. So something that we will prove later, right? That we may have a local explicit form uh, whenever this is non-zero, but whenever it is zero, the thing is actually inconclusive. So you cannot say whether thing will, I mean, one cannot conclude that it is existing or not existing. Both can happen. For instance, consider this example, fxy, uh, fxy equal to 0 for this f of x, fxy. So this is in R2, right? So look at this curve, right? For this curve, uh, consider this point 0 comma 0 in this curve, and you differentiate this with respect to the y variable, which is minus 3y square, and the evaluation of this at 0 comma 0 is 0. Okay, so fy 0 comma 0 is 0. So we are looking under this condition, right? So at 0 comma 0, we have fy is 0. So it is not satisfying this condition, but we can actually write it as a graph of this function in a neighborhood of 0 comma 0. So there is a explicit form of writing this function in the explicit form, right? We can write y as x over 1 over 3 here, right? That is possible in a neighborhood of 0 comma 0, though this y partial derivative is 0. And another example to show that the other possibility can also happen is look at the x and y axis. So the union of x and y axis in R2, that is given by this equation fx comma y is basically is given by the equation xy equal to 0, right? Xy equal to 0 is the union of the axis, that, right, x and y axis. So if you differentiate it, partial differentiate with respect to the y variable, what you get is x, and this is non-zero for x not equal to 0, right? So whenever it's non-zero, you actually have a neighborhood of x naught not containing 0 because away from 0. So you take a neighborhood of your, so in any neighborhood of x naught which does not contain 0, so don't go up to 0. If you fall short of 0, then this is a explicit form. This is actually so can locally this function will express this equation fx, I mean xy equal to 0, because y is anyway 0, so gx is 0 will do the mapping, right, of y not equal to 0. Whereas if you include x not equal to 0, then there is no g in any neighborhood of x naught such that you can write y naught as a g of x naught. Okay, because when you take x naught equal to 0, you are in that intersection of the two axes, right? In that case, you cannot locally invert. So you cannot find an explicit, you cannot write y as a function of x. So this is the 0 cases in general. So what we are now going to prove is whatever we just showed you, that they are locally graph of some function, right? Is in a more general theorem under this condition that the y partial derivative is non-zero. So whenever y partial derivative is non-zero, you can actually conclusively conclude uh, that you can actually have an explicit form. So the function originally might be given an implicit form, but locally you can write it. You can write one as a function of that. So in this case, you can write y as a function of x whenever the y partial derivative is non-zero. So that's the statement. So omega is a subset of Rm cross Rn, okay, and f is a map from omega to Rn. Okay, so here we are, just for convenience sake, we have divided. So f, usually our function f is from Rm to Rn, right? Some two things. So for convenience sake, we have divided the domain Rm as product of different m and n. Okay, think of like that, where the second where the range is same as the second Cartesian product. So f is a map from omega to Rn, right? Is more or less, you can think of this as a map in Rm cross Rn and projecting onto, but not it's not a projection map, but I'm just saying that it's mapping to Rn. And the assumption that we make on f is that it's continuously differentiable. Now, if you take any x naught comma y naught in the point omega, so in this case, what it means, x naught is coming from Rn and y naught is coming from Rn, right? So x naught comma y naught in omega is such that f of x naught is 0, and this n cross n matrix, the determinant of this is non-zero, so it's non-singular. If this happens, then there is a neighborhood u in Rm. So there is a neighborhood of x naught in Rm, call it u. So x naught you see is in Rm, right? So there is a neighborhood of x naught in Rm, and there is a function g on that neighborhood u mapping to Rn such that g of x naught is y naught. So what it is saying that this y can be expressed as a function of x naught. So you can find a function g to Rn such that the second variable can be written as a function of the first variable. This can be done for all elements in the neighborhood that you found. Further, we actually have that fx comma gx is 0 for all x in u, right? For all x in u, fx comma gx is 0, and this g is continuously differentiable. So given an f, you can obtain given an f which could be in the implicit form, you can obtain a neighborhood u and a function g where g is the explicit form of that function in that domain u. Okay, this is what we are going to prove. So that is under this assumption that if you are going to write y as a function of x, the derivative of f with respect to the y variable should be non-zero. I mean, the determinant of that matrix should be non-zero. So proof, you define using the little f, you define a capital F. So originally we had a little f which is from omega to Rn, right? F is from omega to Rn. What we do, we define a capital F from omega to Rn cross Rn. That means now f is a, so both the domain and the range are the same dimension, unlike little f here, right? This is m plus n dimension, this is n dimension. So when I say m plus n dimension, I mean the where not about omega, but where omega is sitting. So here now f is from omega to Rm plus n, which means range is also has the same dimension where omega is sitting. So how do you define this capital F? Capital F, x is coming from Rn, y is coming from Rn. It's define it as x comma fxy. So f was already a map from omega to Rn. So the second coordinate is in Rn, no problem. X was already from Rn, so its first coordinate is in Rn. So define this map fx comma y as x comma. So when I say I here, I mean identity matrix. So I of x is x. I is the identity matrix from on Rn. Okay. So I of x is x. So fx comma y is x comma fxy. So define capital F like that. Now, if you write down the Jacobian of this capital F, which will be an m plus n cross m plus n matrix, which will be this, right? This is the first m elements. Then this is the next. So this is the first m rows. In the first m row, you will have up to the m column, you have the identity matrix, and then all of them are 0. Then here you have the derivative with respect to the x variable. Here you have derivative with respect to the y variable, right? This is the Jacobian matrix of this capital F. If you think of this as a two variable function where they treat each of this tuple as one element, then this is what you get, right? The simplified way of writing this m plus 1, m plus n cross m plus n matrix, right? And what the determinant of this? The determinant of this is precisely I times I multiplied by this matrix, and this is 0 anyway. So this is precise. So the determinant of this is precisely the y derivative of f at x naught comma y naught, right? So the determinant of this is same as dy of fa. So I don't know what is a. We didn't have a here, right? What I mean here, a is the x naught and y naught. Okay, so this a here is actually x naught comma y naught. So dy of f x naught comma y naught. So we have assumed, so the theorem in the statement of the theorem, we have assumed this is non-zero, right? This is non-zero, this is non-singular, this is non-zero. If this is non-zero, jf x naught comma y naught is non-zero, because this is non-zero. So determinant of this is non-zero. So jf, so Jacobian of this capital F is non-zero, right? And what more do we have by definition? F of x naught comma y naught. F of x naught comma y naught is x naught comma 0, because f of x naught comma y naught is 0. That's given to us. F of x naught comma y naught is 0 for this x naught y naught, right? So capital F of x naught comma y naught is actually x naught comma 0. So capital F of x naught comma y naught, it looks like is the projection onto the first m components, right? But only for this point x naught comma y naught, not in general, right? In general, it thing. So the value, value of f of x naught comma y naught is x naught comma 0. Now by the inverse function theorem, where so that we just proved, you can find a neighborhood w around x naught comma y naught and a v around x naught comma 0, which is the image element here, such that this capital F such that it is bijection and there is a inverse, right? It is invertible, right? That's what inverse function theorem tells you, that there is locally they are invertible. So you actually have an open set containing these 2 points, such that and so let's call that inverse as G here. So G is the inverse of the capital F. So capital G is the inverse of capital F, which is from V to W, and we had shown in the theorem that it's actually continuously differentiable. So G of fx comma y is x comma y, right? Because they are inverse to each other. This is by the inverse function theorem. And to apply inverse function theorem, all the hypotheses of the inverse function theorem are satisfied, which is what we have verified here. The Jacobian at this point is non-zero, and the image of that point is x naught comma 0. So whatever was a there is x naught comma y naught here, and this is f of a here in our case. Now this G is a map from V to W, where G is a map from actually domain sitting in Rm cross Rn to Rm cross Rn, right? So G also can be seen as 2 components, where the first component is an m tuple, second component is an n tuple, right? So G1 is the m tuple, G2 is the n tuple. So G1 of f of xy. So if G of f of xy, Gf of xy is Gxy, because this is the inverse. They are inverse to each other. They are right. They are inverse to each other. So and G has these 2 components, which means G1 of x comma y, G1 of f of x comma y will be the first m component, which is x, and G2 of fx comma y is the last n component, which is y. So this equality is also obvious from this whatever we had here by the inverses to each other. So remember this, G1 of f of something is x itself, and G2 of f of something is y itself. So they are actually kind of component wise inverse, you see. So that's what I am letting you. So now you look at take that V that we had, right? The V we had in Rm, right? We had V, which is V is a open set containing x naught comma 0. X naught comma 0 is sitting in x naught comma 0 is sitting in Rm cross Rn. So when we say V is an open set of x naught comma 0, it's a subset of Rm cross Rn. But x naught comma 0 is sitting in Rm cross 0, right? So I can take the intersection or the projection of this open set V onto the Rm space, right? That's what I'm doing, and I'm calling that as my U. So U is just set of all x in Rm such that x comma 0 is in V, because V is now V is a subset of Rm cross Rn, right? So I've just looked at kind of projected it to the Rm copy here, and that will be an open set which will contain x naught, and you define G from this U to Rn as G2 of x comma 0, the second component of the capital G that we had here, right? G2 is a map from Rm cross Rn to Rn, right? So G2 of x comma 0 is what you define as G of x comma 0. Okay, you will see why we are defining this later. It will be very clear why this choice, right? What happened? That is an obvious choice to do. Okay, so then by definition G is C1, because we have already seen that capital G is continuously differentiable. So G is continuously differentiable in its respective domain. So, and here is just a projection of that domain. So little g is also continuously differentiable. And G of what is G of x naught? G of x naught is G2 of x naught comma 0 by definition here. And G2 of x naught comma 0, what is x naught comma 0? X naught comma 0 was the image of f of x naught comma y naught, right? By the definition of, right? F of x naught comma 0 is x naught comma 0. So x naught comma 0 is replaced by f of x naught comma 0, which is nothing but y naught by what we have observed here. G2 of f of something is the second argument, which is y naught here. So g of x naught is y naught. This is, so we have verified all these statements. Under these conditions, we have obtained a u now, which is a neighborhood of x naught, and we have obtained a little g such that g of x naught is y naught. Now we need to show these two, that for all x in u, fx comma gx is 0, and we need to show that, and this also we have shown, that g is c1 is also we have shown. So what remains to be shown is only this, that x belongs to u. So for all x belongs to u, fx comma gx is 0. Okay, everything else is proved. Okay, so for that, to prove that statement, that fx comma gx is 0 for all x in u, let's observe some things. So if I take an element v1 comma v2 in v, right? If you remember, this v was a subset of rm cross rn, right? So this is an rm cross rn element, right? So it's an open set of that. So then there is a unique w1 because v and w were chosen such that f was a bijection, right? So if for any v1 comma v2 in capital V, there is a unique w1 comma w2 in capital W such that v1 comma v2 is the image under w1, image of w1 w2 under f, right? Because that's how we chose w and v to be, right? Now what is the, but we know that v1 comma v2, right, is f of w1 comma w2, because that is how that, and that's how we have chosen w1 comma w2 as the pre-image of v1 comma v2 under f, capital F. And by the definition of capital F, this is nothing but w1, identity of w1, right? I w1 and f of w1 comma w. This is the definition of capital F that we have started with, which means v1 comma v2 is this. Now you see, this is the first m tuple, this is the second n tuple, this is the first m tuple, n tuple. So this equality implies that w1 is actually v1, So if you start with a v1 comma v2 in capital V, you have a unique w1 comma w2, but whatever we have just obtained tells you that this w1 is actually v1. So this implies that w1 is v1. What happens to g of v1 comma v2? Because if w1 is v1, g of v1 comma v2, if you remember, is the inverse of this capital F. So g of v1 comma v2 should be w1 comma w2, but w1 is actually v1. So g of v1 comma v2 is v1 comma w2. Okay, so what is g1 v1 comma v2? So therefore, what happens? So G has two components. We said G1 and G2, right? The first n components and the first n and the second n components. So the first so if G of V1 comma V2 is V1 comma W2, then G1 of V1 comma V2 is this element which is V1, and V1 comma V2 is f of G V1 comma V2 because these are inverses. F of G V1 comma V2, but G of V1 comma V2 is G of V1 comma V2 is V1 comma sorry, what am I saying? Yeah, uh, G of V1 comma V2 has two components, G1 of V1 comma V2 and G2 of V1 comma V2. G2 of V1 comma V2 is here, G1 of V1 comma V2 is V1 here, from whatever we have said here, right? So V1 comma V2 by the invertibility of F and G is Fg V1 comma V2. G of V1 comma V2, as I showed here, G of V1 comma V2 has two components, G1 comma G2. Yeah, right. G of V1 comma V2 has G1 comma G2. G1 becomes V1, G2 comma V2, V1 V2 is here. Okay. So V1 comma V2 is actually f of V1 G2 V1 comma V2. Now for all x and y, so this is something we have, whatever we argued here is true for V1 comma V2. We already know that f is bijective and invertible in V and W from W to V. So for all x comma y in V here, f g x comma y is, because they are inverse to each other, f g x comma y is x comma y, right? And u was just the projection of V the the Rn copy, right? Hence for all x in U, we have fg x comma 0, that is, in particular if we put y equal to 0, so fg x comma 0 is x comma 0, right, which is true because they are inverse to each other. So what is x comma 0? X comma 0 is fg x comma 0, but g has two components, g1, g2. So this is f of g1 x comma 0 and g2 x comma 0, right? And what is g1 x comma 0? G1 x comma 0 is actually the first component, x1. So g1 x comma 0 is x, and g2 x comma 0 is by definition the little g. So g2 x comma 0 is little g. So f of x comma gx. And by the definition of capital F, what is f? It is just the identity of x, which is x, and then f of x comma gx, which is f of x comma gx, right? So this tells us that f of x comma gx is 0. Why? Because we started with x comma 0. We have obtained here x comma fx comma gx, which means the second component here is 0 for all x in u. So for all x in u, fx comma gx is 0. So the uniqueness of G follows from the uniqueness of the inverse map G, okay, because the G was defined in terms of G2, and so the uniqueness of G depends on the uniqueness of G2, but G2's uniqueness depends on the uniqueness of capital G, and that depends on the uniqueness of the inverse of capital F, which is all fine. So this is so we have done with this, we have shown whatever we need to show in the implicit function theorem. which basically tells us that if you have a function in whatever form fx comma y going to something, then locally you can write one of the second argument in terms of the first argument, under this condition that the partial derivative with respect to the second argument, that matrix is non-singular. Okay, so basically an implicit form can be locally written as an explicit form. Okay, so with this we are done, and in fact with this we are done with the course as well. Okay, thanks a lot.